Okay, so thanks for inviting me to give this presentation tonight. We'll be talking about lucky imaging results using the 13-inch Schuppmann telescope at Stellafane and the 6-inch Warder and Swayze refractor at Mount Wilson. My name is Thomas Sporick. I've been a member of the Springfield Telescope Makers for since the late 80s. So a brief outline, we'll talk very briefly what is Stellafane, what is a Schuppmann telescope and why do we want to use a Schuppmann, some recent improvements we made to the telescope, very briefly the 6-inch Warner and Swayze refractor at Mount Wilson. And we'll talk a little bit about the lucky imaging technique. There's not enough time to really get into the details of a how-to, so we'll just skim over the process. And then we'll see some latest results, including some high dynamic range imaging and some ancillary results. So briefly, what is Stellafane? Strictly speaking, Stellafane is Latin and Anglo-Saxon for shrine to the stars. And it's the name of the clubhouse of the Springfield Telescope Makers in Springfield, Vermont. So the upper right picture, that pink building is, that's strictly speaking, that's Stellafane. And again, that's our clubhouse. In the picture, upper picture on the left side, that white building, it's called a turret telescope, where the actual building is the telescope, where the optics are outside and the observers are inside. So if it's cold in the winter, you can go inside and get out of the cold, or if the mosquitoes are around in the summer, you can go in and close the door and not be bothered. Even though that the name of our clubhouse is called Stellafane, because we have our annual telescope making convention every year in the summer for many years, the name has been come to be associated with that convention. So the bottom picture is a picture of our telescope making competition on our hill in Springfield, Vermont. You see that it's a nice sunny Saturday morning, and everyone has their telescope set up for our competition. So the name can be associated with both our clubhouse and the general convention. And Stellafane was started by Russell Porter, who's a native of Springfield, Vermont. That's him on the right side polishing a telescope mirror. And if you're interested in learning more about him, there's a biography by Burton Willard, one of our club members, which you can get used online. And Russell Porter started a mirror making class. The first class in Springfield was August 17th, 1920. So we've just celebrated recently our 100th anniversary. Although the club officially didn't get going until December 7th, 1923, and the first convention was held on July 4th, 1926. So those 100-year anniversaries are coming up. And perhaps Russell Porter is best well known for drawing his famous cutaway drawings of the 200-inch telescope on Palomar. And that's one example there on the right. And one thing about Stellafane is history is very important to us. Here's two pictures separated by several decades, taken from about the same location, and you notice that they're basically the same. So now we got into why or what is a Schuppmann telescope. Schuppmann telescope is a bit unusual design. Most telescopes we're familiar with are either refractors or reflectors. The Schuppmann is kind of a combination of both, and we'll get into some of those details. Although we just have time to skim over those details. If you really want to get into it, you should buy this book written by Jim Daly, one of our members. And he's basically the world's expert on building Schuppmann telescopes. And the left side is a picture of Jim with a 14-inch lens he made. So this here on the right side is our picture of our Schuppmann telescope, and I put over some cartoons of the optics. So very basically, and I hope people can see my cursor, up here on the left, we have a 13-inch single lens. The light comes from the left, focuses down the tube to the far end of the tube on the right to a 2.5-inch field mirror. which it's not flat. It does have a curve, and that mirror re-images the objective onto a middle mirror, which is called a Mangan mirror up here at this point. It's about 8 inches in diameter, and it's a back surface mirror. So both the front and the back have been polished and figured, and their reflective coating is applied to the back. So the light actually passes through the glass, bounces off, and then comes back out of the glass, and then to our right angle mirror and our eyepiece or our camera. And basically our goal when using this telescope and when we're imaging either the planets or the moon is to capture the most subtle details possible on our target. So we want to minimize anything that would degrade that. So this is a list of some of the advantages of a Schuppmann telescope. And we will go into some details in the next pages on each one of these. But basically, it's a perfectly achromatic refractor, so it has no color. It has no central obstruction to cause scattering. It can correct for atmospheric dispersion, which is very important right now with Jupiter and Saturn being so far to the south. Back surface reflections scatter less than the front surface, and smaller mirrors scatter less than larger mirrors. Also, the mirrors, the surfaces of the mirrors are easier to make than a standard refractor lens. So one problem we have when you use a lens for a telescope, as many amateurs of course know, is chromatic aberration. And in this schematic here on the left, we have a single lens with the light passing through it from left to right, and the light is split into its colors where the blue is focusing short and the red is focusing long, so you cannot get a nice focus of your image. This plot here on the right shows in the x-axis is the wavelength, so 400 nanometers is blue, 700 nanometers is red, and right now we're looking at this blue line where the y-axis is the focal length. So this shows us that the focal length for every wavelength is different, so you can never focus this with this lens. So one solution that engineers have come up with over the years is to add a second lens. And this does a little bit better job. We see our colors come to a better focus. And right now we're looking at this yellow line. And again, we're looking visible is from 400 to 700. And while it is better than the blue line, it's still not very good. So we can get a better focus, but not a perfect focus. Another solution is to add a third lens. And now we get an even better focus. And now we're on this red line. And we see in the visible band, we're getting a pretty good focus. Not completely perfect, but pretty good. However, we've now made this lens very complicated where we have 1, 2, 3, 4, 5, 6 surfaces that we have to make. And they also have to be not only high quality in and of themselves, but they have to be very high quality with respect to the shape of each other. So this is very difficult to make. So this again here is a schematic of our Schuppmann. We have our 13-inch lens. The light comes to a focus on this field mirror, and as we saw in the previous schematics, the colors have been separated. So at this point on this field lens, all the colors are separated and we have a very poor image. This field lens with this curve re-images the objective onto this Mangan mirror, which is a back surface mirror. And then the light passes through the glass, hits the silver, comes back out of the glass. And if it's all aligned correctly, out comes perfectly corrected white light. And then we put our camera or our eyepiece. So we're able to fix all of the color that goes into the objective. We take it out with the Mangan mirror and the field mirror. Another advantage of a Schuppmann, it has no central obstruction. Here's a picture of a young person with their telescope they made at Stellafane. And we see, as within all Newtonians, we have the secondary mirror, and that secondary mirror scatters light, and scattered light reduces the contrast, which degrades our very low contrast features that we're trying to see. Up here on the upper right, we have a simulation of a telescope with no central obstruction. This is what a star would look like. And this is on the lower part is what a star would look like with a central obstruction. And we see there is more light in the outer rings. And this shows that it would reduce contrast. So the fact that we don't have a central obstruction is an advantage. Another advantage is that we can correct for color put in by the atmosphere. Right now, Saturn, for example, is in Sagittarius. It's very low on the horizon for the northern hemisphere. And as the white light from Saturn passes through the atmosphere acts like a lens, and it separates the color. So we're getting this smearing effect where the colors are in physically different locations. However, in our Schuppmann, our field mirror and our Mangan mirror corrects for color, but they don't necessarily know or care where the color comes from. So by adjusting the tip and tilt of the field mirror, we can correct for color not only coming from the lens, but also from the atmosphere. So we can correct, in this example, Saturn, we can make it a perfectly corrected color image as if it were high in the sky. Another thing we want to do to record very faint details, very subtle details, is to reduce scatter. So this basically shows that the scatter of back surface mirrors is less than the scatter of front surface mirrors. We also have the fact that the mirrors are smaller than the primary objective. In this case, the largest mirror is 8 inches, while the primary objective is 13 inches. So this mirror has much less scatter than a front surface mirror for an equivalent aperture as if it were a Newtonian. Also, the individual optics on the Schuppmann are easier to make because they're smaller and they're all spherical, and the sensitivity in wedge is greatly reduced. So while there are a great number of surfaces, the individual surfaces are relatively easy to make. And again, this is a picture of the Mangan mirror, the back surface. And that's Jim Daly, the author of that book, inspecting it. So this is a painting on the side of a wall in our observatory, cutaway drawing as if Russell Porter had done it by one of our members. So again, here's our 13-inch primary single lens. It brings the light to a focus on the 2.5-inch field mirror, which then re-images the primary objective onto our 8-inch Mangan mirror back surface, and then the light comes to our fold mirror into our eyepiece or our camera. And then here's a picture of the observatory, which is a roll-off roof. The roof is rolled off in this particular picture. And then up here in the front, of course, is our 13-inch lens. So while this is not necessarily improvement, one thing you have to make sure if you're trying to image the faint details on the moon or the planets is to make sure your optics are clean. Because even if you have all low scatter optics and they're dusty, the light would scatter off the dust and reduce the contrast. So this is Jim Daly here, and he's literally using Bounty towels and Windex to clean our objective. And he spent 40 years working at Lincoln Laboratory for MIT on optics, so we trust that this is the correct procedure. And here's a picture of our nice clean lens. Also, a recent improvement is we had the Mangan mirror recoated. As all mirrors, the coating eventually degrades, no matter how well you take care of it. This mirror was originally coated back in 1995, so over about 25 years, the coating started to degrade. So we sent it out for a new coating. And here on the left is Jim Daly inspecting that coating. It just has come back with a nice fresh coat. And on the right here, he is installing it in its mirror cell. And here he is inspecting it. This is our mirror cell for the mangan. It's at the top, the center port of the telescope up at the point. And this is our tip tilt adjustment for fine alignment. And whenever you put your telescope back together, of course, you want to make sure it's all aligned properly. This picture on the left is inside of our focuser box. This is the field mirror we've been talking about. However, there is a cover over it to keep dust off it. And we have a little target on that mirror. And so we shine a light laser into the eyepiece, and we make sure that it hits the center of the field mirror. So we're sure that our optics are all nice and aligned. So another improvement we made is of we installed a Leo stop. Unfortunately, let me try to get this working because I'd like to show a video. Okay, unfortunately, it's not going to let me show the video. This is if it was working, would be a live video of Saturn. So imagine when you're looking at Saturn at high power, Saturn would not be stable as we see it here, but it would be wavering, continuously wavering. And as you look at it, sometimes it would be blurry, and sometimes for half a second or a second, it would snap into a good seeing, and then it would get blurry again. That's what this video is essentially a live image of Saturn. Now, just a little bit of background into why we want a Leo stop. And it's really something that all amateurs know. We all basically know that on a night when the seeing is not very good, a small telescope will give a better image than a larger telescope. So this is a little bit of the background science to this, and we're not going to get into any details, but there's a scientist who studied the physics of the atmosphere named David Fried, and he has a couple of papers here. This is back in the 60s. I have these papers if anyone would like to see them. Basically, he studied the properties of the atmosphere that cause bad seeing. And what he did is he came up with this equation where P is the probability of imaging a good image. And in this particular case, we're only talking about short exposures on the order of milliseconds or tens of milliseconds. But what this equation shows is the probability of getting a good image is a function of the diameter of your optic and this feature called R0. And what this equation shows that as your diameter goes up, because it's a negative exponent, the probability goes down. And as amateurs, we know that as your telescope gets bigger, your seeing gets worse. And it also shows that as this term R0 gets bigger, your probability also gets bigger. And this R0 is a representation of the size of the atmosphere cells that are in front of your telescope. And the bigger the cell, the better the seeing. And this is a plot of that equation for various sizes of telescopes. So for example, with a 12-inch telescope, on average seeing, in this particular plot, the x-axis is the size R0. So on the left, the seeing is bad, where R0 is small. On the right, the seeing is good, where R0 is large. And the y-axis is the number of images, very fast images, again, on the order of milliseconds, you need to take in order to get a single, quote, good image. So for a 12-inch telescope, in average seeing, for example, if we follow this line, you need to take about 3,000 very short images to get one good one. However, if you convert your telescope to an 8-inch telescope, you follow this line to the green line, and you now only need to take 10. So this shows that as we reduce the aperture, the number of good images greatly increases. And this is just a mathematical representation, again, of what all amateurs know. On poor seeing, large telescopes give worse views than small telescopes. So one way to change the size of your telescope, of course, is to put an aperture stop in front of the main objective. However, in this particular case, we did not want to do that, so we added an aperture stop over our Mangan mirror. And in this particular case, when you put an aperture stop over an image of the objective, it's called a Leo stop. This L-Y-O-T is a French word pronounced Leo. So what we did was we made a metal aperture with a hole which can flip in and out of our optical path. So when this metal hole is in front of our optical path, as it shows here on the left, our telescope is equivalently 9 inches. And when we want to use the full aperture, we rotate this as it shows here on the right, and we now have a full 13-inch telescope. And this is a picture of shows Jim Daly. We're basically, instead of doing this by electronics and motors and such, we try to do it as the people might have done it 100 years ago with rods and levers and things. So we're basically installing a long push-pull rod. And so now we have this little handle. As we push this in, the Leo stop will go into the optical path as it shows here on the lower right. And as we pull this out, the Leo stop will be removed from the optical path as it shows here on the upper right. So we can convert our telescope from 13 inches to 9 inches with just a pull of this lever. And that's basically it on the Schuppmann. Here, this is a picture of the 6-inch Warner and Swayze refractor at Mount Wilson with a Brashear lens. This is one of the first nighttime telescopes installed up on Mount Wilson. Again, 6-inch f/15. It's basically kept in the original state as it was originally installed. It still has its weight-driven clock drive, as close-up picture here on the right. In the pedestal, there is a weight which is risen. It's raised up to the top of the pedestal by this 100-volt DC electric motor, which is original. It then weight slowly drops and it spins the governor, which runs the clock drive. It doesn't necessarily work as nice as a modern clock drive electronic, but it works well enough to do some imaging, and it's a very nice telescope. Of course, Mount Wilson is a very good site. So now we'll just briefly talk about Lucky Imaging, and this one sentence here on the left is somewhat important. It's Lucky Imaging is the process of capturing and saving many short exposures as rapidly as possible and selecting the good ones to be aligned, averaged, and enhanced in post-processing. And so the steps in this process are we capture the raw images is the first step, and that's what the work we're actually doing at the telescope. And then steps 2 through 5 are post-processing with the computer later. We pre-align them if they're jumping around a lot. We then select the good images and save the good ones and align and average them. We can do some post-processing and then whatever other post-processing we'd like. And we'll briefly go over these steps in the upcoming slides. And again, this is that same picture, or that same movie of Saturn. It should be. Unfortunately, it's not working. But it's just a picture when you're viewing any planet at high power, it's constantly wavering due to the scene. So the first thing you need is a camera which can capture and save images as rapidly as possible. I happen to use cameras from the company ZWO. They have a variety of cameras depending on what you want to do. If you're only imaging the planets are very small. So you can buy a camera with a small chip. There's no point in spending a lot of money for a large chip if you're not going to use it. And these cameras are on the order of $150 to $180. And this camera can take pictures on the order of 200 frames per second and upload them to your computer. And for that capability, less than $200 is a pretty good price. However, if you need a larger chip, for example, when imaging the moon, they have a chip, this particular camera with a large chip for about $1,000. However, if you'd like to image the entire moon, a camera with a large chip is very necessary. It would take too many, you'd have to take a montage with many dozen samples, sub-pictures with a small chip. So if you're interested in imaging the moon or any large target, you really need to have a camera with a big chip. And this is on the order of 1 inch, corner to corner. Having said that, this camera can upload pictures at the full frame at about 15 frames per second. And even so, for $1,000 for a camera that can do that, it's not a bad price. And depending on what you're doing, you may need a filter wheel and filters. So they also sell that. Again, this is just what I happen to use. There are other companies to choose from. So the first step is to take your images, and the program that I use to run the camera is called Fire Capture, and this is free. A gentleman in Europe, basically it's his hobby to write this, and he makes it available to the community for free. And he does answer questions, and there are communities where people can post questions, and experienced users will answer them. And the goal of this program is to run your camera. So this obviously is this is our full frame with the large camera with the large chip, and obviously this is the whole gibbous moon in one piece. We then can control our camera. We can control the gain, our exposure. We can one nice thing with this program is it saves all this information in text files, so you don't have to actually take any notes while you're busy at the telescope. It saves everything for you to look up later. So you can say, tell that you're imaging the moon, what filter you're using, and you simply push a button to start recording and stop, and it will then take images as fast as it can and save them onto your hard drive. This is a status box where it tells you how many frames you have taken and how many have been saved. This is a histogram of your image, which we'll talk about a little later, and some other information. So basically the output of this program is a video, which is just a string of several hundred or several thousand individual short exposures. Then sometimes, depending on the quality of your hard drive, your telescope drive, perhaps your planet may be wobbling around a lot. For example, when using the Warner and Swayze, it's got 110 or 120-year-old gears, and that the planet tends to wobble around a lot. So you can then run it through this program called Planetary Image Preprocessor, which is also free. And all this does is takes your video that you initially saved, and it lines up the planet so the planet is not wobbling around too much. So your output is that same video with the planet more stable. Now, this is a bit of an important aspect to this entire process. We said that the whole point of lucky imaging is to take a lot of short exposures and then pick out the good ones. And that's what this program does. I happen to use AutoStacker, and this is also free, written by, again, someone in Europe, and they make it available to the community. And there's community groups that answer questions, and you can either post questions to the community group or post questions to the author, and usually within a day or so get an answer. So what you do is you load in your video, you analyze it, and what it does is it looks at every image in this string in this video. In this particular case, this video has 4,976 individual images of Saturn. And after you analyze it, it makes this plot here where the x-axis is simply the image number, where image number 1 is on the left and image number 4,976 is on the right. And the y-axis is the quality, where higher is better. So this, if you look at this gray line represents that the quality of your image is constantly going up and down, and this is what we're seeing when we look at a planet at high power and we see it wavering in real time. This is just a numerical representation of that effect. This green line is the same data, simply plotted on the left as the best and on the right as the worst. So after we make this plot, we have to decide how many of these images we want to keep. Again, we took a video of 4,976 images. And in this particular case, I've decided I want to keep 1,024. And then we set our alignment boxes, which is we're telling the computer which features we want to use to align these images. And then we simply select stack. The program will select the best 1,024 images, align them, and average them, and save the single image. So the output of this is a single image that is the average of those n, in this particular case, 1024 images. And the last part of the process is wavelet processing. I happen to use Registax for this. This is also free. And you have these sliders here, and you basically can choose which layers you would like. Basically, layer 1 is the small features, and layer 6 is the large features. You can denoise and sharpen and adjust these sliders however you'd like, and you can improve your image. So this is a pretty nice image we have here of Saturn. You can see the nice, very clear bands. We even have that green pentagon that's at the pole. We can see the Cassini division, and you can even see the planet through the Cassini division. So this is, at the end of this entire process, we've gone from our video of those several thousand images of a bunch of blurry Saturns to this one final result. But so basically that's the lucky imaging process in 10 minutes. So now we'll talk about some results. So this is Mars from the summer of 2018 using our 13-inch telescope at Stellafane. The seeing was not that great that night, so we had it stopped to 9 inches. And if you recall from that particular apparition of Mars, there was a planet-wide dust storm. So in the visible light, you basically could not see any features. Mars was just blank. However, in the infrared, was able to look through that dust and we could see features. So this particular case, we used an infrared filter, and we had this series of Mars, where you can see the features pretty nicely. And you can see over the course of this few minutes, you can see a little bit of a rotation of Mars from the lower left to the upper right. And also keep in mind that the seeing in Vermont and the East Coast in general is in general pretty poor. There's a reason that there are no professional observatories within 2,000 miles of the East Coast. So the fact that we get images of Mars like this from Vermont makes us very happy. And here's a close-up from that apparition of Mars, one when the telescope was set to 9 inches, one from when the telescope was set to 13 inches. Obviously, the 13 inches is brighter. Perhaps there's some more detail in the 9-inch version. It's somewhat subjective. This is an example or two examples of Saturn from that year. It was good seeing that night, so we were using the 13-inch, full 13-inch telescope, and when this was with a red filter. Obviously here we have the nice red spot. And this is, relatively speaking, a pretty nice image of Jupiter. Here we have a sample of Mars, Jupiter, and Saturn, all taken on the same night, July 4th, 2018. Seeing wasn't that great, so we had the telescope set to 9 inches. And this is all at the same scale. So This is the actual size on the sky of Mars, Jupiter, and Saturn that particular night. In general, Jupiter is on the order of probably about 50 arc seconds. So we see that it's very unusual to get Mars to be anywhere near this big, which is, of course, why it's nice to image and look at Mars when it's at opposition, because it's so huge, relatively speaking. Normally, Mars is just a few arc seconds across. This is a series of Jupiter we took in the summer of 2019. And in this particular case, we used the color camera. We see it's a ZWO camera, and this MC, the C stands for color in this particular case. Seeing wasn't that great, so we had it set to 9 inches. And this is a series over about a half an hour or so. And because we do have a Schumann telescope, we're able to use a color image, a color camera. At this particular time, Jupiter was very far south, so we would normally be suffering from the chromatic aberration caused by the atmosphere, but we're able to correct that with the telescope, so we could use color camera. And this is just some blow-ups of some of those images, just to see some better detail. And this is a blow-up of one of those. And that white circle is 1 arc second. So this shows that we're basically getting on the order of 1 arc second, maybe a little less in some of these fine details. And anytime you can do that from the East Coast, that's pretty good. Here's some examples of Saturn. We did some changing between the 9-inch and 13-inch to see if we can get much different. Saturn is a little harder to tell because the details are more subtle. But in both cases, we got that hexagon, that green hexagon at the pole, planet through the gap, Cassini division. A lot of nice bands. Again, this is with a color camera. And we got a blow up of Saturn here. This circle is 1 arc second. So we're getting our bands a little bit less than 1 arc second. That's pretty good. There's another Saturn. This is a series of Mars we did last summer. In this particular case, we used a monochrome camera, which this is indicated here. ZWO is the company, and the MM here means it's a monochrome camera. And the reason we did that is because we wanted to use, in addition to color, we wanted to use an infrared filter. So in this particular case, we had 4 filters, red, green, blue, and infrared. And the red, green, and blue images were combined later to create the color image. So basically, each of these columns required 4 images, 3 images to create the color, and then 1 infrared to create the bottom image. And then we see some rotation that's on about 50 minutes. You can see some rotation of Mars, and there's a lot of nice detail. So now we'll talk about some imaging of the moon, and we'll also start to get into some high dynamic range imaging. If we look here on the left image of the moon, we see that obviously some of the parts of the moon are bright and some of the parts of the moon are dark. And to a computer, an image is simply a grid of numbers, where low numbers like 0, 1, and 2 represent black. Gray or middle gray is represented by images or numbers such as 100, 101, 102, and the brightest areas are represented by numbers in the 200s. And if you plot those numbers on this chart, where the x-axis is simply 0 here on the left and 255 here on the right, and the y-axis is the number of each of those numbers. So this particular little bump here is because there's a lot of the black. This shows, this is called the histogram, and we set our exposure such that the right tail of the histogram is about in this area. If you go too far to the right, that means you're saturating your image, which is not good. So this we'll call this a, quote, correct exposure. The problem is even though we are getting a good exposure for our bright regions, our darker regions are a bit underexposed. So one solution is to take more than one image. So we can take this center image, which is a longer exposure, and so the moon appears to be brighter, and we're getting more signal, more information in our middle dark regions. We can take an even longer exposure where we're now saturating our brightest regions, but now our darker regions have a lot of nice signal. So in this particular case, the dim image was 1 millisecond, the center image was 1.5, and the right image was 2 milliseconds. So then what we do is we combine each of these images with some software, which plucks out the good regions in each particular exposure into one single image. And the result is something like this, where we can get a lot of nice detail across the entire moon, even though that some of the areas are dark and some of the areas are light. So we call this a high dynamic range image. And this was taken with the Schumann telescope at Stellafane. And because the image of the moon is so large, we had to take a montage of 6 pieces. So basically the size of the chip is that square I'm kind of drawing now. And we had to take 6 of these and then put them together later. So this raw image is 7,500 pixels across. And if you printed this out at 200 dots per inch, the moon would be 3 feet across. And you could make this print and it still looks very nice. You can't see the pixels at this size. So printing this on a small computer screen, unfortunately, doesn't give it justice. It really needs to see it printed out on a large size. So that's the results from the Schumann. We'll now talk about some results from Mount Wilson. Of course, an advantage of Mount Wilson is it's got some of the best seeing in the entire world. So here's some images of Mars taken from the summer of 2018. And all of the color images from Mount Wilson are combinations of red, green, and blue, which we'll talk about a little bit more shortly. So this is a series of Mars. We can see Mars rotating from left to right over the course of this couple of hours. Here's a picture of Jupiter with the 6-inch refractor and Saturn with the 6-inch refractor. One thing we noticed that Saturn here has this blue tinge. And that comes from the fact that the particular design, the optical design used for this lens, has a greater chromatic aberration than normal. In this picture, we see kind of the fact that the blue and the green and the red are kind of spread out evenly. Unfortunately, with the 6-inch refractor at Mount Wilson, the blue is spread out much more than the green and the red. So normally we would use a red filter with 100 nanometer bandwidth, which is typical, a green filter with 100 nanometer bandwidth, which is typical, and we would like to use a blue with 100 nanometer bandwidth. The problem is that the chromatic aberration in the blue is so great that with 100 nanometer bandwidth, you can't focus the telescope. So we have to use a narrow band filter in order to get a focus in the blue part of the spectrum. The disadvantage of that is we're cutting out most of our light, and that we have to pay the penalty of a longer exposure. Fortunately, unfortunately, the longer exposure gives the atmosphere more time to blur the image. Remember back when we were talking about the equation on how many images it takes to get a good image, how many total images it takes to get one nice one, that was contingent upon the fact that we're taking short exposures. Well, when you're blocking off most of your light with such a narrow band filter, we now have to take long exposures, and that means that most of our images are going to be blurry. This is the advantage of Mount Wilson, is that the seeing there is so good that even with, I believe, the individual exposures for the blue were on the order of half a second, and they still look good because the seeing is so good at Mount Wilson. But these are some typical samples of Jupiter and Saturn with the 6-inch refractor. And these, especially this Jupiter image, is probably diffraction limited, meaning this is about as good as the telescope can do. In order to do better, you need a larger telescope. This is an example of 3 images of Jupiter taken with 3 different telescopes on Mount Wilson. The left image was with the 6-inch Warner and Swasey. The center image was with a 16-inch Meade, a modern telescope. And the right image was with the 60-inch, the first of the large telescopes installed at Mount Wilson. And we can see that, in my judgment at least, I would say that the best image is the center one, taken with the 16-inch telescope. Now, unfortunately, these were taken on 3 different nights, so the overall seeing could have been different on each night. However, we also have the fact that we recall the larger the telescope, the worse the seeing. So this may be showing us the fact that there is an improvement going from 6 inches to 16, but as you get bigger than 16 and go to 60, the 60 inch is just too big, and it starts to get degraded because of the large aperture. If we remember our plot here, plot of the equation, which indicates the number of images we have to take in order to get a single good image, how rapidly the number increases as we increase our aperture. Regardless, these are 3 pretty good images of Jupiter, all from Mount Wilson, and all combinations red, green, and blue. So now we have some examples of some high resolution images of the moon from the 6-inch Warner and Swasey telescope. These are all done with a red filter. We have a straight wall here on the left and Theophilus region on the right. And these images, the scale was set such that these images are showing the most detail that the telescope is capable of showing. Here's the Stoffler region on the left and the Cassini region on the right. This is an example of a comparison using the quote standard correct exposure, which is shown on the left side, versus the high dynamic range image on the right side. So the histogram, as we talked about before, where the quote correct image has the tail ending about here, that's the histogram of the left image. And then we took 2 additional exposures that are brighter and combined them to make the image on the right. When you get to this part of the number crunching, we're now getting into art more than science. So there's really no right answer. It's just what each individual person happens to like. This is an example, again, of this is a full moon taken at Mount Wilson with the 6-inch Warner and Swasey. This is the highest resolution that the telescope is capable of. This image can easily be printed 3 feet across and still look very nice. And for this image here on the right, which is a blow up of the crater Plato, all I did was crop this piece and blow it up to this size. And you see that there's all this nice detail on the floor of Plato. And this is a typical standard test for seeing. If you can see detail on the floor of Plato, it means you have a pretty good seeing. And considering the amount of detail, the seeing here is pretty spectacular. So just imagine how this, if we were to print this entire moon at the scale that Plato is, the moon would be several feet across and still look quite nice. And again, that's the advantage of the seeing at Mount Wilson. And here's another sample of typical exposure versus high dynamic range. Whatever one you like is fine. It's just art now. Here's another example of a third quarter moon. This last particular set was done with a 4-inch f9 refractor with a blue filter. Same with this one. This is a 4-inch f9 refractor, and this just shows a comparison of the apparent size of Jupiter and the full moon. I happened to take an image of the moon and an image of Jupiter. I cut and pasted them together just to show how small even the biggest planet is compared to the moon. Here, Jupiter is about 45 arc seconds in diameter, and the full moon is about 2,000 arc seconds. And here's some recent images of Jupiter with a 4-inch f9 refractor. And again, this is all with the lucky imaging technique. These are combinations of red, green, and blue images. And this dot is 1.4 arc seconds, which is the resolution of a 4-inch telescope in green light. So basically, anytime we can see features this big means we're at the limit of the telescope. And I would say that's, considering the size of some of these subtle features, that's about where we are. Here's a recent image of Jupiter and Saturn on the same night at the same scale. Here's a set of Jupiter in actually 5 different filters. We have the color, which is a combination of red, green, and blue. We then have infrared, and then we have methane, which is a common filter people image Jupiter with. There's a lot of methane in Jupiter's clouds. And this, again, these white dots represent 1.4 arc seconds, which is the resolution limit of this telescope. And unfortunately, this was a movie of Jupiter rotating, which doesn't want to work. And this is the last set of the moon, and this just shows an example of how powerful this high dynamic range and lucky imaging technique is. The right image is the previous image we saw from Mount Wilson, and the left image is a result of a movie taken from using an iPhone through a telescope eyepiece. I did not take the movie, I downloaded it off the internet, but then I did the number crunching. And while these images don't compare as far as the fine detail, considering how simple the setup was for the left image, that's a very high quality image. So it just shows lucky imaging and the high dynamic range technique. It doesn't take much to do some really good work. And for my last picture here, the high dynamic range technique isn't exclusively for astronomical targets. This is a picture of stellophane. The standard exposure, which I snapped with my phone, is on the lower right. and the upper left is a nice autumn image, which I ran through the high dynamic range process. And again, this is getting to the fact of the aspect of art. And so it's, if you like it, it's good. If you don't like it, it's bad. You can really bring out the colors and the details. So if anyone has any questions.
Yeah, I have a couple questions.
Sure.
First of all, you have the mirror where you have it on the back. What kind of glass is it going through that it, and does it absorb any kind of color or whatever? Because it's going
So,
through the glass.
sure, yes, that's correct. However, keep in mind that for refractors, refractors do the exact same thing. So yes, there is always some minor absorption, even in a refractor. And you also have to keep in mind that the surface has to be anti-reflective coating, because reflections, typically each reflection that on a surface that is not coated is about 4%. So let's just say you send light through a lens with no anti-reflective coating, you lose about 8% just in reflections. But the absorption, the same as a refractor, is very, very minimal.
Yeah. Okay.
And in this particular case, with the Mangan mirror back surface, because you see that the back surface here is painted, we're able to use silver, which normally would tarnish in the air, but because there is no silver that is exposed directly to the air, we're able to use silver and it will last 20 or 30 years, as opposed to I don't know the exact how long a silver mirror would last in the air, but it would tarnish within weeks or months, unless it had a sophisticated coating.
Okay. And I have a couple more questions real fast. At Mount Wilson, you showed that refractor there. Which dome is that in?
It's
Yeah.
in the small. It's a small clamshell dome, 100 or so feet to the west of the 60-inch dome.
Oh, okay. I'm gonna have to check that out eventually here. And also, then on the picture of the moon, when you're showing the really high quality, how small of an object can you actually have you measured like how small of an object you could you could actually see? You're saying, I mean,
But just 1 second. 6-inch. A 6-inch telescope can resolve something on the order of like 3/4 of an arc second. I haven't done the math. I don't know what 3/4 of an arc second comes to at 250,000 miles, but it's probably a lot more than people think. It's probably in tens of miles.
yeah, but still.
I just haven't done it. It's a simple equation. I just haven't done it.
Okay, no problem.
But
If you want to ask a question, just go ahead and unmute your.
Okay, well, I have a question too. It looks like this process is very well suited for objects like the moon, Jupiter, and Saturn. I was just curious if anything of this type was used on either the moons of Jupiter or Saturn, and also maybe Mercury.
Yes. Perhaps the moon of Saturn are on the difficult side because they're so dim. I do know that people with somewhat large telescopes on very good seeing sites, they have done good work on the moons of Jupiter. And yes, you also can do this for Mercury and Venus. And you also could do it for Uranus and Neptune, but you need a large telescope on it with a very good seeing, because those those planets are so dim, your exposure has to be relatively long, and you're giving the atmosphere time to blur your image. So once your exposure starts getting into the hundreds of milliseconds and more, this whole process doesn't work.
Yeah, that's what I would expect. Okay, thank you.
Yeah, let's hear it for Hubble.
I have a question, if I may.
Shoot.
Sure.
Very interesting talk. A lot of stuff I was unfamiliar with. With respect to the tilting of the mirrors, do you introduce any astigmatism into the system by doing that?
No, it's not tilted very much. Actually, just a second. Where's that picture? Well, yeah, tilting of this mirror here. Oh, I should show. Yeah, tilting of this mirror here. It's not tilted very much, so no. Actually, if you tilt it too much, yes, there will be astigmatism, but then the color will be all messed up. So it would be very obvious. So we actually, outside the telescope, in this particular schematic, which would be to the right, a little bit to the right of this mirror, sticking out the back, there are two small knobs which control the X and Y tilt. So what you do is you point it at a star, and then literally in real time, you can adjust the tip and tilt of this mirror to make the color disappear.
So that's the control law you use. You just do it by eyeball.
Yes.
Interesting. Okay. Thank you.
And if you want to really get into the gory details, you have to get the book and go through all the equations and such.
Oh, I'm going to do that for sure.
And I happen to know Perry Ramakoulis of Wilman Bell. They are going to be reopening under a new owner shortly.
Oh, and interesting. And I don't know, it's just as a matter of interest, because in passing, I worked at Autonetics for some 25 years. And although Dave Freed had left the Anaheim campus by the time I got there, he came back to Placentia and opened his own company. And I didn't really know him, but I knew a ton of people that did know him. So I thought that was very interesting. When the minute I saw that, I said, "That's Dave Freed."
Yes, he's basically famous for what's called, this R0 is called the Freed parameter.
Yeah. Well,
This R0 term, it's called the Freed parameter. Yeah, there it is.
yeah. Well, Autonetics before I got there had a lot of very smart people.
And those papers are easy to look up. I looked these up by myself. There's no big secret to finding these.
Yeah.
But if somebody wants them, I can send them. I have them as PDFs.
Oh, yeah. Thank you. I'll look them up. I'm sure I can find them.
Thomas, I was interested, what are the main things that go into the fact that seeing is not very good on the East Coast?
Well, the fact that you have, well, I'll start by why it's good on the West Coast, and that's because you have thousands of miles of smooth Pacific Ocean, which does not disturb the air. So as the air comes onto the West Coast, it's still not disturbed, nice and there's not a lot of small scintillations. But then as it travels over the continent, it has 3,000 miles to get of mountains and valleys and heating and cooling to get all jumbled up. So basically, that's why, for example, Hawaii has very good seeing. That's why the seeing down in the observatories in South America, it's the same effect. All you have the nice smooth air coming off thousands of miles of water. So you tend not to have good seeing when you have a lot of land in between you and water,
Oh,
as
okay.
far as the direction of the air movement goes.
Oh, okay, because the air is traveling from west to east across
Right.
the country. Okay.
So it
Great,
gets
thank
all
you.
jumbled up as it comes across, and then when it travels across the Atlantic Ocean, it then kind of gets recalmed, and then as it goes on to Europe, it gets jumbled up again.
Okay. Great, thank you.
Okay. We want to thank you for your time and effort that you put